Refinancing?
We spent our entire lecture talking about it, almost. Okay, very quickly. Refinancing is you have a deal with a mortgage company, another mortgage company, you go to them, you say, well, this is my deal right now, can you give me a better deal? If you give me a better deal, you take it. If you don't give me a better deal, you don't take it. It's really as simple as that.
You know what the criteria they use to, if you want to refinance, what criteria do you need to have so that you can
The
get
NPV today, you reduce your NPV, the amount that is to be paid back.
Okay.
So you figure out how much you owe the company, and you go to them and tell them, give me a lower rate. Usually they will give you a lower rate because this company will pay the remaining amount to the first company, and that will be their loan to you.
Okay.
So you get a lower rate, obviously, but the problem is closing costs. You usually have to pay closing costs, and that's where you have to factor that in. So as long as closing costs are not substantial, yeah, you can always refinance. I don't know what impact it has on your credit history. That's another separate question. All right, good. Any other question? No politics today. No. I'm going to do early voting and be done with it. Okay. So, I think last class we started discussing a problem where you have a fertilizer plant. The fertilizer plant is making fertilizer. That means it's taking in raw material, making fertilizer.
We didn't.
But then it's pumping out some ammonia.
Oh, we did talk about that.
Okay? Sorry?
I thought, no, I was just like, we didn't talk about that. And I'm like, okay, we didn't talk about that.
So the problem is this concentration of ammonia, let's call it C outlet, it's greater than C minimum. So C minimum or I guess C maximum, what do we call it?
I thought it was C.
C star? The C star is allowable concentration. What is the allowable concentration? C allowed?
CS.
Okay, so CS we said it's 25 ppm. The problem is the C outlet is higher than CS, and so you have to put in a scrubber. Okay? And as I told you, so you put in a scrubber. Now the way that I can even tell you how the way the scrubber is designed. The way the scrubber is designed is you take in this gas, and you actually have packing here, and on this packing you spray nitric acid or sulfuric acid. So the sulfuric acid reacts with ammonia in this packing, and you basically get your ammonium sulfate. And then of course the concentration of ammonia goes down, then you have a second packing, you also spray on that, third packing, spray on that, and finally you get your concentration of ammonia out. Okay? So now, let's call this C. I think last time we just called it C, and that led to a little bit of confusion on the optimization. Let's be clear what the C is. So the C is the C out minus delta C, right? And to be precise, let's say minus delta C scrubber. So this delta C scrubber is a change in concentration that occurs inside the scrubber. Okay, does it make sense? And what we're trying to figure out is, now we have to design the scrubber. We have to design the scrubber, which basically means we have to decide what is the rate of pumping of acid. And we have to design that, which means we basically have to figure out how much delta CS we are aiming for. The problem is the C outlet is obviously not fixed because the plant manufacturing, a lot of changes that can happen, a lot of which can adjust the set point. So let's say this is lying in the range of C min to C max with equal probability. Okay? And because we don't know this concentration, if you knew the concentration exactly, then of course it would be straightforward, right? If C out is exactly known, then you change so that this difference equals to what? C allowable, right? So if C out is exactly known, then it's easy. You just make this to be C allowable. No, sorry, C safe. So you make it equal to C safe so that what is coming out, you don't have to pay penalties, right? And so you choose delta CS to be C out minus CS. The problem is we don't know C out exactly, and that is why it's an optimization process. Okay? The C out is going to lie in this range of C min to C max with equal probability. Does that make sense? Yeah? Any questions? Yes.
What's the difference between the two CSs? Are they the same? Right there, then you have C out minus delta CS equals C.
No, so delta CS is C scrubber, CS is the C safe. So that they are completely different.
Change that.
Is that a mass
Let's
balance?
just call it delta C. We don't have to put a scrubber there. Because delta C is delta C. So let's remove the scrubber.
So C out is going into the scrubber and
So
delta.
C out is the outlet from the plant. It's going into the scrubber. The scrubber reduces the concentration by delta C. And you want the final concentration at the outlet to be C safe. So from there you can figure out how to design the scrubber, yes.
So is our end goal to design the scrubbers so that we spend as little money as possible, where like if it hits Cmax?
Exactly. So we want to spend as little money as possible. Because think about it like this. You could say, well, you know what? I'm going to take the maximum possible value of C out. So let's say I say C out equals to C max. So I design my scrubber so that delta C equals to C max minus CS. In this case, you never have to pay the penalty, right? What's the problem here? You may be over-designing the scrubber because designing a scrubber costs money, right? On the other side, if you say, well, I'm going to not do this, if I had delta C less than this, then there's certainly a possibility that every once in a while I have to pay penalty. So that's where I have to make a decision on where to design it so that I kind of optimize those two. Okay? So it's a different kind of optimization problem than what you're used to, because in this case, the need for optimization is coming from uncertainty. Okay? Does it make sense? Because things are uncertain.
How
Does
do
it
you
make sense? Before I actually, yeah.
how do you know that C out is? Are you saying C out has to be between CM minus?
So C out is just what comes out of the fertilizer plant.
Right.
Now the problem, if we don't know that exactly, because there will be variations. Whatever plant you make, there will be small changes in temperature, small changes in concentration, small changes in rate constants. Many of those effects will combine together, so the outlet concentrations will always range. You will never know the exact value, right? Just like even the temperature here, the AC, we try to set the temperature with AC, but still temperature varies in a range, right? Nothing is exact. Nothing is exactly where you design it to be. Yeah? So far so good? Everybody's with me? Okay, so now of course the question is, we want to minimize our cost, so we have to come up with a cost function. So let's see what's the cost function. So the cost function has two parts. What is the part for the penalty? The penalty is straightforward. Let's just say it's some constant beta times the concentration that comes out, which is C out, minus delta C minus CS. So it's some constant beta times that difference. If C out minus delta C is greater than CS, right? And equals to 0 otherwise. Right? So the penalty you have to only pay if the concentration after scrubber, this concentration is larger than the safety limit. You have that, then you pay penalty. Yeah, make sense? And we are assuming that the penalty is simply linearly proportional to this difference. Yeah?
What's your beta term?
Beta is just a rate. It's just $1 per concentration. It's just a rate. So basically your penalty, so last time I was drawing a diagram for penalty. The penalty is 0, and then it starts increasing linearly. So that's our assumption for the penalty, right? It is what it is. It's what the government imposes, right? More than likely the picture will not be like that. More than likely the picture will be like this. There will be a sudden jump, and it will be like a much higher expression. So if you exceed, you have to pay a certain penalty, and then it will be a further increase if you're further away from the set point. Okay? But we are making a very simple approximation that this is what the penalty function looks like. Okay? This is actually not that bad, it's realistic. The question is, what about so this is the cost for, now the cost for scrubbing. That is a very complicated expression because, to really figure out the cost of scrubbing, we have to design the scrubber. But I assume that to be a very simple expression, which is some proportionality constant divided by C out minus delta C. The idea is that if the outlet concentration, the smaller it is, the larger will be the cost. Right? So it kind of captures that very simple aspect that is certainly accurate. But does it really capture everything? No, by no means. It is certainly not a good approximation for actually calculating the cost of scrubber. But I just want to use a very simple function that will allow us to solve the problem. Okay? So this is in some sense really the weakness of this analysis. Everything else we are doing is actually quite realistic. The problem actually is quite realistic. This cost model for the penalty may be fairly realistic. This is really the weakness. But this is the best we can do. Otherwise, I'll have to start designing the scrubber for you, and from there calculate the cost function. So I don't want to do that. But this does capture certain aspects. So the factor, so what it captures is, if you're looking at the concentration, this is the C outlet. Let's just say you plot C out minus delta C. It goes to infinity as this number goes to 0. Right? So basically behaves something like this.
Wait, you're plotting C out versus delta C?
No, the costs.
Okay. Oh, cost versus, okay.
So one cost basically goes down in this direction, one cost goes up. So you can right away see that there has to be some optimum solution, right?
So those two costs are different?
They both are cost. This is cost for penalty cost. This is scrubbing cost. Okay? All right, make sense?